Yeah, I would say that I'll try to replace him in the best way I can, but I'll do my best. Okay, so hello everyone. My name is Giuseppe Lucente, and as you can see from the title of this talk today, we will discuss together how supernovae can be seen as efficient laboratories to probe axions and other weakly interacting particles. Indeed, due to the larger temperatures inside the supernovae, they can be used to probe axions with masses up to about 100 MeV. And this topic is very hot nowadays. Indeed, there are a lot of new developments that we will discuss together. So as Maurizio has already said, this talk was supposed to be given by Pierluca, but unfortunately he had some problems, so he's very sorry, and I'll try to replace him in the best way I can do. So before characterizing the axion production inside supernova, let's briefly revise the mechanism of a core collapse supernova. So a core collapse supernova is the final phase of a massive star, which mass larger than about 8 solar masses, which becomes unstable at the end of its life. Indeed, in these massive stars, the nuclear fusion produces heavy elements in onion-like shape and with a central degenerate iron core. Now, since the iron is the most stable nucleus, it cannot be burned. So due to gravity, it starts to collapse, but when nuclear densities are reached, it becomes uncompressible. And okay, it becomes uncompressible and it bounces, and a shock wave is generated, transforming the implosion into an explosion. And this is the way in which a core collapse supernova happens. Now, after the supernova, what remains is a proto-neutron star cooling via neutron emission. And in order to have an idea of the typical conditions inside a supernova core, we need to see that the density inside the supernova is about 10 to 14 grams per centimeter cubed. The temperature, as I said before, is very large, of about 30, 40 MeV, and in principle, there can be also very high magnetic field with an intensity of about 10 to 15 Gauss. So these are the typical supernova conditions that we have to have in mind when we characterize the axion emissivity. Now, the main role in a supernova explosion is played by neutrinos. Indeed, the 99% of the released energy is emitted by neutrinos and antineutrinos of all flavors, with typical energies of about 15 MeV on a time scale of 10 seconds. Indeed, neutrinos are produced inside the supernova core, then they are trapped, so they diffuse, and they are emitted from a last scattering surface through the so-called neutrino sphere, with an energy of about 15 MeV. And this standard picture has been confirmed from the detection of a neutrino burst in 1987. Indeed, in February 1987, there was the so-called supernova 1987A, which is the milestone for supernova physics, since it is the first and only event from which we detected supernova neutrinos. Actually, we observed a bunch of events through 3 different water Cherenkov detectors, Kamiokande, IMB, and Baksan. And actually, the signal was obtained due to inverse beta decay, in which an antineutrino and proton produce a neutron and a positron. And actually what is measured is the energy of the produced positrons. And through these measurements, the standard picture of the supernova physics was confirmed. Now, these are very few events, so the statistic is not too large, but in this way, the standard picture was confirmed. And now, starting from this standard picture, we can try to constrain the production of new particles. So if novel and weakly interacting particles are produced inside the supernova core and free stream, they will steal energy from the core. So they will reduce the energy emitted by neutrinos, and they will shorten the duration of the associated neutrino burst. So by requiring that the duration of the observed neutrino burst from supernova 1987A must not be shortened by more than 1/2, leads to the approximate condition that the half luminosity must be lower than the neutrino 1 for typical supernova conditions. So what we usually do now is that, since we have a lot of supernova models, supernova simulations, we take data at 1 second after the core bounce, we compute the axion luminosity, and we impose that it must be lower than the neutrino luminosity taken at 1 second from this supernova simulation that we consider to constrain the Hall parameter space. So this is the general constraining method to constrain the Hall parameter space. And from now on, I will show you some examples to show you how we can constrain Halls interacting with different standard model particles and a wide range of masses. So let's start considering axion interacting with nucleons. So first of all, I will show you which are the production processes and then some way to constrain these axions. So for many years, it has been considered that the dominant production channels for axions interacting with nucleons is the bremsstrahlung represented here. But in order to characterize the emissivity, one needs to model the nuclear interaction among the nucleons which are involved in this process. And for a lot of years, the main way to model this interaction was the so-called one-pion exchange, in which the nuclear interaction was modeled with the exchange of one pion. And in literature, usually the mass of the pion was also neglected. Now, there was a development in the last few years, in particular in 2019, a work by Pierluca, Maurizio, and Alessandro went beyond this one pion exchange approximation, adding more details to include details on nuclear physics and many body effects. So, for instance, they considered the pion mass, they considered also an effective mass for the nucleons involved, and also many body effects, including multi-body scatterings of the nucleons inside the supernova core, and they added also the contribution of two pions exchanges. Now, all these corrections reduced the emissivity of the nucleon bremsstrahlung of about 1 order of magnitude. And in addition, in the last years, actually, it has been shown that actually there is another process which is competitive with the nuclear bremsstrahlung, which is the pion conversion. So this is essentially the Compton-like scattering of a pion on nuclei, on nucleons producing an axion. And actually, there were some papers in the 90s discussing the possibility to produce axions through this process. But in the years, this process was overlooked, since it was supposed that the population of pions inside supernovae was suppressed, since the thermal abundance is very low, the thermal abundance of pions inside supernovae. However, there was a paper in 2019 by Sanjay Reddy and Fore, who showed that actually the population of negative charged pions can be enhanced inside supernovae due to their interactions with nucleons, through which they acquire a chemical potential which enhance the population of pi minus and suppress the abundance of phi plus and pi zero. So even if the density of pions is about 1% of the abundance of nucleons inside supernovae, this is sufficient to lead to the dominant production channel inside supernovae. And what do you, I mean, okay, so you mean the computation related to the pion abundance inside you were asking? The problem there is the really know where, as you say, no? I mean, these improvements is related to the you made an best way of some improvements, right? You know, like many body effects, some beyond one higher stage, so maybe you have exchange of a raw meson, yeah. No,
Then one should be no, but so here the premise so for neutrinos is subdominant. So okay. Correct. The axiom participation, right? That's control. The part that's the interaction, it's you know. I agree. There are several problems, but it is unfortunately it's subdominant. Yeah. But then the
among the two between the two processes, this is the dominant production. Yeah. Actually, it is a factor of two larger. So I mean, they can compete. This is the dominant process, but so the. Okay.
There's been a lot of work done to understand this which is relevant to supernova, even with the P matrix, like some approaches that are more like the phase shift and the experimental, and it's like in the end, in this paper with Pierluca, like there were some different. In the end, it wasn't bad. The agreement is still like it's not something we are completely under control. But there have been follow lines. Yeah. Don't go ahead. That's you can compare with the matrix
and they agree.
It goes very well. The paper is discussed. There's a very pertinent question, very pertinent, concern, but it agrees very well with this. I don't remember exactly how well the factor of something. Again, this calculation corresponds to just a protection from experiment and dressing of the light. Well, originally this was calculated, this graph, this diagram was calculated like I think you are going to calculate, I calculated at one point, but it's just that key, like with a coupling file, and then that protection to give the long right. So then there's been some because there are constant interactions. Yeah. So nowadays, this protection for the action, how they're concluded. Just using protection and moving to other experiments and then
the spin-dependent part. The spin-dependent part. Okay. So it's not so simple. I mean, the context is not spin-dependent. So the file exchange. But file exchange is not so bad if you would test on the peripheral part of potentially files to be confused major spin-dependencies. But they've got this short bench also part, which undoes some of them. But also in some older paper, we used to compare this with actually experimental data on interact of ion branch from different branch of ion axion. It's clear to that. So there are various ways of getting to an order.
Already around 2000, 2003, I think writing Sanjay introduced this low energy comparison low energy data from this category. Because you try to separate the axion part from
what you could compare with ion.
Compare with the back. And then but so somehow it's
but also in intermediate, how you know the correlations between them, but there are many uncertainties. So I'm also a bit skeptical of the higher power too.
Yeah.
Yeah, are we really so sure how many pilots there are? I mean, it depends on
it depends. I mean,
it depends on the effective energy.
I mean, there is this paper by Sanjay and Fore who says that the uncertainty is, I mean, they expect a quantity of about 1%, 3% inside the supernova core. So, yeah. Actually, they say that due to the interaction between pions and nucleons, what happens is that the energy cost is reduced because there is this viral expansion in. Okay, sorry, you can. It's the same. I mean, yes. Yeah.
And go beyond the it's correct. And they find that, and somehow in the supernova, you definitely, if you don't go high,
yeah,
too high, then you can stop it. And they say they claim, and that's fairly accurate. Like this is a proper way to do it. It's possible. It's well justified in the factor.
The question of what's the energy profile in the future? How much energy do you need to invest to create the because that under control. So I'm not expert. So you wrote the paper.
Yeah.
One typically uses the omega. Basically that's it, to understand the scaling. But then the normalization are somehow fixed with the energy data, which is never up here. But yeah, that's why but they depend on the
mechanical potential of ions, negative
Yeah, actually, the chemical potential of ions in this work by Sanjay and Fore is exactly equal to the difference between the chemical potential of neutrons minus. Yeah, and it's of the order of 100 MeV, between the temperature and 100 MeV. And they say that all these calculations are valid until the chemical potential is lower with respect to the mass of the pion, because otherwise there will be condensate, essentially. And if there is condensate, the pions cannot contribute to the production of.
But I think the like places a little water, the temperature is very sensitive to the temperature of the production. So there is good reason to believe that most of the production doesn't happen where maybe condensation like that. So obviously we're not very this is a difficult thing, right? But we are all sometimes it's experience, right? So like it's not that we take this book.
I mean, yeah, they started working on 2020, I think, more or less, and then developed all this calculation. I don't know if we can go on, or are still any comments, something? Oh, okay. Yeah, and actually then there was a huge developments related to this process. Indeed, actually in the following years, there have been new developments. For instance, also with some colleagues here, and for instance, Choi added the contribution of the contact term interaction. And in addition, there was also the contribution in 2022 of the delta mediated term. So all this correction increase the emissivity of a factor of few with respect to considering just this diagram here. So now to consider the production of axions inside supernovae, one has to consider both the processes. And indeed, by considering both the processes, one have that this is the production spectra of the axions inside supernovae interacting with the nucleons. In particular, here you can see the spectrum for two different values of the masses. In the low mass case, so this 20 MeV mass, you can see a bimodal shape of the spectrum. And the first peak is related to the nucleon-Bremsstrahlung at a peak of about 80 MeV, while the second peak is related to the pion conversion, and it is at much larger energies since due to the pion rest mass. On the other hand, for masses larger than the pion mass, there is only one peak that you can see here, since the nucleon-Bremsstrahlung is completely negligible with respect to the pion conversion. And just to mention, here you can see in this colored region, and this red region is much larger than this one, and this represents the fraction of ALPS produced inside supernova and trapped inside the gravitational potential of supernova. Indeed, they need to have a large kinetic energy in order to escape for the gravitational potential, and so this is what we actually can see at large distance with respect to the supernova. So now, in order to constrain the parameter space, one has to compute the axion luminosity, as I said before. So here you can see the axion luminosity as a function of mass for a fixed value of the axion proton coupling, since here we are assuming that axions interact only with the protons, and we assume that there is no interaction with the neutrons. And as you can see in this plot, in the low mass limit, the pion conversion gives a luminosity which is a factor of 2 larger with respect to the nuclear Bremsstrahlung, while for even larger values of the mass, the pion conversion becomes more and more dominant, since the Boltzmann suppression is more efficient in the nuclear Bremsstrahlung with respect to the pion conversion. So by imposing that the axion luminosity must be lower than the neutrino one at 1 second after the core bounds, we can exclude the light blue region shown here. And here you can see that if we consider only the nuclear Bremsstrahlung, the bound is weaker, and it is relaxed at masses larger than about 30 MeV, so larger than the supernova temperature. While considering also the pion conversion, the bound becomes stronger, and it is relaxed at masses larger than about the pion mass. So another thing that I want to stress about this plot is that we cut it at couplings of 3 × 10⁻⁹, since in order to obtain it, we assume that axions are in the free streaming regime. So their mean free path is much larger with respect to the stellar radius, which is about 10 kilometers for a proton-neutron star. So now we are working on moving on. So it would be useful to generalize this bound to see what happens also in the trapping regime. And actually here you can see, and this is taken from a paper that it is going to appear, the axion luminosity as a function of the axion proton coupling for 3 different values of the axion mass. So now let's see together this plot. You can see that in the for low values of the axion proton coupling, the luminosity increases as the square of the coupling constant, since axions are in the free streaming regime. But then the luminosity reaches a peak, and then it starts to be suppressed. Why does it happen? Because when we increase the axion proton coupling, axion starts to be interact so strongly inside the supernova core that they are trapped inside the core, so they diffuse and they start to act just like neutrinos, and they are quasi-thermal emitted from a spherical surface, which we call the axion sphere, which is the analogous of the neutron sphere. And in this case, the luminosity scales as the 4th power of the temperature of the emitting surface. So since as the axion proton coupling increases, the radius of the axion sphere becomes larger and the temperature decreases, this explains why the axion luminosity decreases for larger values of the axion proton coupling. So here you can see the behavior for 3 different values of the mass. And for each value of the mass, we can exclude all the couplings for which the axion luminosity is larger than the neutrino one at 1 second after the core bounds, represented by this horizontal black line. Now, here, when we go through this trapping regime, not only production processes are important, but also absorption processes. And the absorption processes which are important depends on the considered mass. Now, in the case of light halves with mass much lower with respect to the pion mass, both the processes are important. Indeed, for energies lower with respect to the pion mass, the dominant absorption process is the nuclear Bremsstrahlung, while for larger energies, the pion conversion is possible, is kinematically allowed, so an axion can be absorbed to produce a pion, and the dominant absorption channel becomes the inverse pion conversion. On the other hand, for masses larger than the pion mass, we can consider only the inverse pion conversion, while the nuclear Bremsstrahlung is always negligible. So let's see how the production spectrum changes if one increases the axion-proton coupling. We have seen that in the free streaming regime, as represented here by the solid thick line, we have a bimodal shape with two peaks, while in the trapping regime, for instance, here for couplings of the order 10 to -5, as represented by this thin solid line, we have a quasi-thermal spectrum at much lower energies. Why does it happen? So in the free streaming regime, we have this peak which is related to the pion conversion, but we have seen that for a given coupling, for energies larger than the pion mass, the absorption via pion conversion is more efficient. So as we increase the axion-proton coupling, this peak tends to decrease because these axions are absorbed, as you can see in this dashed line. And for even larger layers of the coupling, this peak completely disappears, as you can see here. Regarding the nuclear Bremsstrahlung, this is a quasi-thermal process. Therefore, the peak of the Bremsstrahlung is related to the temperature of the region where axions are emitted. And since we have seen that if we increase the axion-proton coupling, the emitting region becomes it's shifted towards larger radius where the temperature is lower. This causes a shift in the peak of the spectrum, shifting from about 60 MeV in the free streaming regime down to about 6 MeV for couplings of the order 10 to -5, where axions are emitted in a region where the temperature is about 3-4 MeV. So now we have seen how axions can be produced. Oh, sorry, can you hear me? Okay, now yes. Can be produced inside the supernova core. So now can we ask ourselves, okay, they are produced, they can arrive on Earth. So would they give an observable signal on Earth if they interact only with the nucleons? The answer is yes. Indeed, there was a seminal paper by Engels in the 90s, which showed that actually axions arriving on Earth can excite. Do you want to make a question? Okay. Can excite the oxygen inside the water Cherenkov detectors, and then after the excitation of the oxygen, a photon would be produced with energies of the order of 10 MeV, and therefore this photon could trigger a signal in water Cherenkov detectors, just like we have seen in the neutrino case with the positrons. So recently, this interaction, the cross-section for this interaction has been revised, and here you can see the cross-section for the excitation of different levels of the oxygen shown here. And so one can evaluate the number of events induced by axions arriving on Earth. Now, if axions were produced during supernova 1987A, they could have induced a signal inside the water Cherenkov detector. So if one assumes that the 12 events observed in Kamiokande second were related to neutrinos, the presence of axions would have induced a large fluctuation of the background, which is a Poissonian process. And so in order to place a bound on the L parameter space, one can impose that the number of events must be lower with respect to the fluctuation of the background. So what happens now? Here, this delta TA is actually the time window in which we can observe axion signal arriving on Earth. And for masses lower than about 30 electron volt, axions will arrive with neutrinos, and so the time window will be about 12 seconds, so the same as the neutrino signal. While for larger masses, due to their mass, their arrival will be delayed, and the signal will be spread with an expression written here. So in this way, one can constrain the parameter space just requiring that the induced events must be lower than the background. And so here you can see an overview of the constraints that can be obtained using the strategies that I have just discussed. In particular, here you can see in blue the bounds on obtained from the energy argument, energy loss argument, so the cooling bound, and in green, while the one obtained through the non-observation of events from supernova 1987A. In particular, the cooling bound excludes values of the coupling between 10 to minus 9 and 10 to minus 6, more or less, while the events exclude values of the coupling larger than 10 to minus 7. So altogether, we can see that the supernova bounds can exclude the QCD action bands for masses larger than about 10 to minus 2 electron volt. And so here I can summarize all the bounds related on the coming from supernova and constrain the axion proton coupling. So now I will close this part related with axions interacting with nucleons. So if there are additional questions or comments, we can discuss together. Okay, so. Okay, actually what we expect is that here the bound would be a bit shifted. I mean, of course, it depends a bit on the model that you assume, because of course the contribution for interaction with the nucleons could change the position of the bound here, but here we are proceeding with just assuming a case-VZ like model. So, yeah. Model, yeah. Yeah, but the order of magnitude is, I mean, that's the. Nice.
Could you say that ESAs, where you have a public you're right, okay, a lot of studies are on the part that added, which is the left side is the final part. I think they are supposed to right? So yeah, so they then reduce because then they are probably better than I think you did some nice with
yeah, I mean, I could. Yeah, this was the band I was referring. I have the backup slide, which I can show. This one, Maurizio. This one, I write in the. So this is assuming the possible. So this is the way in which it can change. As I was saying before, just this band. There is another question by Georg.
One was clear, was it that slow in the beginning?
Oh, this comes actually from the possible observation of, I mean, the possible axial dissociation of deuterium from in snow experiments, actually. So 2021 or 20.
What they did, they looked at no data, and then they consider the axions can be produced in the sun.
Yeah.
In the sun. This process, like the same for Xeno,
Exactly.
And then detecting the same process, so they actually constrain GAP managed the N.
Yeah, and
they got this bound, which is
yeah,
very strong.
actually, this lies only on, is based only on this axion nucleon coupling, and it was I mean, it was a BRL in which they discussed this, and was based actually on the same process through which axions are produced in the sun, but so the inverse process, so the axial dissociation of the deuterium inside the snow. Yeah.
And you assume that the photon coupling
Here we are assuming that there is only the axion proton coupling, so there is no axion photon coupling here. So we are assuming that there is no interaction with photons. Yeah. Other questions or comments? Okay, so connecting to what Georg asked us, so related to possible interaction with photons, let's pass to the second part of this talk, in which we can consider axions interacting with other standard model particles. So let's consider axions interacting with photons. So here, let's see together which are the possible production channels, which are different, of course, with respect to the previous one. So we have the Primakov conversion, which is the conversion of a photon into null of the same energy in the electric field of charged particles inside the supernova core. And then we have also the photon coalescence, which is the annihilation of two photons in a medium of sufficiently high density to produce an axion. And this process can happen only if the axion mass is larger than twice the plasma frequency, which is the effective mass of photons inside the plasma. So these processes can be used to evaluate the production of Alps inside the supernova, and actually from supernova we can obtain different a sizable number of bounds on the AV-Alp parameter space. And indeed, here you can see an overview of the bounds on the AV-Alp parameter space, which show nice complementarity also with other bounds. For instance, with the HB bound that yesterday also Oscar discussed here, but they are very complementary also with laboratory experiments, which can probe only larger values of the axion photon coupling. While if we focus our attention on the supernova bounds, you can see here in dark green the cooling bound obtained using the energy loss argument that I previously discussed. And here this bump here is related to the contribution of the photon coalescence, which becomes dominant for masses larger than about 100 MeV. But we can obtain an even stronger bound using supernova as calorimeters, as actually firstly proposed by Schramm in the 90s, and then recently discussed again by Georg, Andrea, and Eduardo. I think there was no one else in the paper. So by Georg with Eduardo and Andrea, in which the argument is the following one. So if you have axions which are produced inside supernova and then decay inside the mantle, they will deposit energy there. But you have to require that this energy must not be larger than 10 to 50 erg, which is the lowest supernova explosion energy which has ever been measured. So in this way, one can obtain the pink region, we can exclude the pink region shown in this plot. On the other hand, in light green, you can see the bound obtained from the non-observation of a gamma ray signal from supernova 1987A. And now I would like to focus my attention on this bound here, since there are some developments that I would like to discuss with you and show you what happened. So here now we are considering AV-Alps, which can be produced in supernovae through Primakov effects or through photon coalescence. And then after escaping from the supernova envelope, they can decay into the galaxy, into two photons, so they could give an observable signal on Earth. Now, if axions were produced after supernova 1987A, they could have been detected by the gamma ray spectrometer on the solar maximum mission, since it looked for a possible gamma ray signal for 223 seconds after the explosion. However, since no signal was observed over the background, just requiring that the Alp-induced signal must not be larger than the background, one can constrain the Alp parameter space. And actually, this bound was obtained for the first time, I think, around 2018 by Javier, Georg Jekyll, and Malta, but it has been recently revised and updated. Actually, there is a recent analysis about November 2022, in which Sebastian Hoff revised the bound, obtaining similar results. And then in April, Eike Müller, David Marsh, and Pierluca, and other guys from Stockholm updated the bounds, adding for the first time the contribution of the photon coalescence that I previously discussed. And here you can see that the new bound is the red region shown in this plot, which is stronger with respect to the one considering only Primakov, which is the dotted line here. In addition, in this recent work, they have also evaluated the sensitivity of a Fermilat in the case of a future galactic supernova explosion at 50 kiloparsec of distance in the direction of supernova 1987A. And this sensitivity is the red line shown here. Now, they also asked themselves, okay, we have evaluated the sensitivity, but let's ask ourselves, what could happen if we manage to detect a signal? How can we reconstruct the L parameter after the detection of a signal? And in order to answer these questions, they considered two different cases. One case, so case one, considering an axion mass of 1 MeV, and case two, considering an axion mass of 100 MeV. And the main difference between these two cases is that in case one, axions are ultra-relativistic, so they can do a series of assumptions and which simplify the evaluation of the sensitivity and the detection, and through which they arrive to some conclusion that I will show you soon. While in case two, axions are no more relativistic. So in order to understand how parameters can be reconstructed, what they do is to simulate what Fermilat would say in case of a gamma ray signal produced by ALPS. So here you can see the observed spectrum integrated over time on 10 to 5 seconds of the observation time in an energy range from 25 MeV up to 600 MeV, since the energy threshold of Fermilat is about 20 MeV. In orange, you can see case one, and in blue, the case two. On the other hand, in the lower panel, you can see the light curve of the expected gamma ray signal. And in particular, you can see integrated in this case over the energy. And you can see in the solid lines which represent the expected analytical flux, while the dots represent the simulated data. Now, in particular, I would like to stress that these scattered here are related to the Poissonian nature of the signal detected by Fermilat. And the interesting thing is that in case of more massive ALPS, the main difference is that the onset of the signal is delayed since axions take more time to get out from the supernova. But when the signal starts to be detected, essentially there is no time dependence, so it is almost flat. On the other hand, if we consider the upper panel, you can see that the shape of the flux is quite similar, but actually by fitting them through an analytical formula that they obtain in the paper, some important information can be obtained. In particular, here you can see the analytical form through which they parameterize the expected observed gamma ray signal, and this is valid only in the ultra-relativistic case where the mass is lower than about 10 MeV, and depends on three parameters, A, alpha, and omega 0. Now, A is a renormalization factor. Alpha is related to the spectral shape of the produced ALPS, while omega 0 is the average energy of the produced axions. And you can see here that by performing a likelihood analysis, they will reproduce the real values, which are in red, with the measurements, which are shown here in green. So now what it's important in particular is that in this way you can well reconstruct the average parameter and the spectral shape, but if you reconstruct the A parameter, it's very important because it depends on the parameters of axions. So it depends on the coupling and on the mass. In particular, it is proportional to this product, the square of the coupling times the mass. So in principle, one can reconstruct the L parameters, but this degeneracy cannot be broken. So what they obtain is that in the case of the detection of a signal, they would not reconstruct exactly the values of the input parameter, so the real values of the coupling and the mass, but they will find a hint region without breaking this degeneracy. And this is the 1 sigma level confidence level of the hint region, and it's cut here because they say that for larger masses, the assumption they do fail. So you can distinguish the case of massless case, let's say light case in this case until 10 MeV, and larger masses. And indeed, how do they prove this? Actually, they repeat the same analysis considering a larger values of the mass, so case 2, and you can see here that actually there is a very bad reconstruction of the ALP parameters. In particular, they have an extremely large unphysical value of the spectral shape. And in addition, there is a very huge uncertainties of the order of 30% on the renormalization parameter here. So if one detects a signal, in principle, no one knows which is the mass of that ALP. But using the fit they propose, one could at least distinguish between a light case, in which at least a hint region can be shown, can be found, or a more massive case in which the fit fails. So this is another example on how ALPs can be detected and can give an observable signal on Earth. So if there are questions on this part, I can move on. Yeah, actually, yes. Thanks for the question. Actually, what? Okay, so there is, what is a fireball? Essentially, if photons decay, I mean, if you, then you want to add something, if I make some mistakes or so on, please, you can add something. Okay, so if photons decays in a region of high density photons, a fireball could form, and so photons would thermalize in this region, and therefore we will not be able to see a gamma ray signal. And actually, this has been just discussed, I think, 1 month ago by Eduardo Vitaliano and other collaborators. But actually, what happens? These bounds will not be valid because we cannot observe such high values of the energy, since due to thermalization, the gamma ray signal will be shifted at energies lower than about 1 MeV. But what happens? During after supernova 1987A, actually there was the Pierre-Venus Observatory, which was sensitive to these low values of energies of about 1 MeV. So actually, there is a small region of the parameter space, actually in this region here, where this bounds no more works, but actually it can be closed again using the observation of the Pierre-Venus Observatory. So in the end, these bounds, I mean, these regions of the parameter space will be still excluded, but using a different argument. So, for these low values of the coupling, not. Yeah, because the value of the coupling is too low. What you are saying is completely correct, but related to these values of the parameter. So it will change the explanation of the bounds in some sense, because the region will be still constrained, but using different arguments. So, okay. So now we are considering still photon actions. I have still time? Or? Yeah. Okay, so maybe we can look at this other example. So now let's consider still actions interacting with photons, but let's move to another region of the parameter space. Let's no more consider heavy actions, but let's consider light actions. So now they are produced via Primakov effect, not via coalescence because it's subdominant, and they the decay into two photons is no more efficient, but actually they can convert into photons in the magnetic field of the galaxy. And so they could give, in any case, sorry, an observable signal on Earth. So in this context, what happens? We have seen that you need to introduce another concept. We have seen that many neutrinos of ALPS can be produced inside supernovae, and we have always discussed about possible events from the observation of only one supernova explosion, so supernova 1987A. But actually, all the neutrinos which are produced in all the past core collapse supernovae can accumulate and then can reach us with an energy which is redshifted. And indeed, in this way, they will form the so-called diffuse supernova neutrino background, which is isotropic with a peak end. And you can see here, for instance, the diffuse supernova neutrino background for anti-neutrinos. And you can see that if you remember, at the beginning, I said that supernova neutrinos have energies of about 15 MeV. But here the peak is shifted to lower energies at about 1 MeV due to the redshift. So they reach us with a redshifted energy. So by analogy, as we can define a diffuse supernova neutrino background, we can reproduce the same argument and consider also a diffuse axion, supernova axion or supernova ALP background. And here you can see an estimation for the diffuse supernova ALP background in the case of production via, okay, here there is the example of nucleon bremsstrahlung here, and in case of Primakov, which is shown in red. And actually these are evaluated fixing the values of the coupling near the most constraining bounds for each of the two cases. So what happens? We have seen that this neutrino background, and so the supernova background is isotropic, but they travel until reaching our galaxy, and then they can convert into photons inside the Milky Way. Therefore, since it is isotropic, actually what we see in the end is the gamma ray signal with a morphology which is related to the morphology of the magnetic field inside the galaxy. And here, actually, you can see the sky map of the conversion probability, which reflects essentially the morphology of the magnetic field inside the galaxy. And you can see that it is maximum around the center of the galaxy with lower values for larger values of the latitude and the longitude. And actually here you can see also a white dot, which is, I imagine, very simple to understand what it is, because it's actually the position of supernova 1987A, because what I've just told can be applied also for axions produced during supernova 1987A. So one can constrain the L parameter space also in this case after the non-observation of gamma ray signal from supernova 1987A, but actually one can constrain also the parameter space by the non-observation of a gamma ray signal associated with the diffuse ALP background. How can we do this? Actually, this work has been done last year, I think, yes, by Francesca Calore, Christopher Eckner, but also Maurizio and Pierluca and Alessandro. And what has been done is to compare the morphology of the observed gamma rays by Fermi-LAT with the theoretical expectation of the morphology of the ALP-induced gamma ray signal. So here you can see the morphology of the observed signal after 12 years of observation, and here you can see the expected gamma ray signal from diffuse supernova background for a fixed value of the axion photon coupling. And this is valid actually for masses lower than 10 to minus 11, where the probability, the conversion probability is essentially energy independent. So you can clearly see that the morphology of the two signals is very different. So one can constrain the L parameter space by comparing the morphology of the two signals, and in this way they obtained the red region. They excluded the red region shown in this plot, where the hatched region is related to the astrophysical uncertainties. And actually this bound is is stronger than cast, but it is a factor of 6 weaker with respect to the bounds obtained from the non-observation of the gamma ray signal from supernova 1987A. But here, this bound is not based only on one event, but on diffuse, so on a series of all the past core collapse supernova. So this is another way to constrain the ALP parameter space. So if I have just a couple of minutes, I will just mention another way to place a bound, just to show you another form of phenomenology. And so let's change again scenario and consider now how it's interacting only with nucleons and electrons. In this case, axions would be produced in supernova via Bremsstrahlung of pion conversion, as we have discussed at the beginning. But then, so I repeat, we are not assuming now, we are assuming that they are not interacting with photons. So when they after escaping from the supernova envelope, they can decay into electron-positron pairs. What happens in this case? So in this case, if axions decay outside the supernova envelope and inside the galaxy, they would produce positrons but also electrons, but let's focus on positrons. The positrons slow down due to Baba scattering with the electrons in the environment, and then annihilate almost at rest in about 1 million years, depending on the density of electrons inside the galaxy, after formation of a positronium, which is a bound state of a positron and an electron. Now, about 25% of them annihilate after the formation of parapositronium, so producing two photons with energy equal to the 511 keV, so to the electron mass. In this way, they could contribute to what it is called 511 keV line. What is the 511 keV line? It is a strong photon flux coming directly from the galactic center, which has been measured by different experiments, such as the spectrometer on integral. So the question is, can we explain? There is still no clear explanation for the 511 keV line. So the question is, can we explain this with Alps from supernovae? Actually, we have tried to answer this question exploiting the morphology of this signal. So we have compared the Alp-induced signal with the observed signal by SPI in red. And if we give a look to the latitude distribution, there is a good agreement between the signal and the Alp-induced one. But if we give a look to the longitude distribution, here we can observe that we cannot explain the signal with our Alps, since they have a completely different shape. Indeed, the SPI data are peaked at the galactic center, while the Alp-induced signal has a dip at L equals 0 and two symmetric peaks at plus or minus 30 degrees, which is related to the supernova distribution inside our galaxy. So in this case, in order to place a bound on the Alp parameter space, we have to require that the Alp-induced signal must not be larger than the experimental data by more than 2 sigmas. And in this context, the most constraining bit is the one at 30 degrees, where the experimental data are almost flat, while the Alp-induced signal is larger. So here you can see the bounds obtained through the 511 keV line, and values larger than the upper limit. For values larger than the upper limit, Alps decay inside the supernova without giving an observable signal, while for values lower than the lower limit, they decay outside the galaxy without giving a signal. In addition, by reducing the Alp proton coupling, you can see that the excluded region becomes more and more narrow, and we reach a point in which all the production of Alps are not efficient enough to give an observable signal on Earth, even if all the axions decay inside our galaxy. Finally, I would like just to comment that the shape of the bound is almost independent of the mass, and what happens is that when we consider larger values of the mass, the bound is shifted towards lower coupling, since due to the dependence of the Alp decay length on the axion mass. So now, just to conclude, I would just like to stress this other possibility. So now we have considered the axions produced by galactic supernovae. What happens if we consider extragalactic supernovae? So axions will decay into electron-positron pairs, they will annihilate, they will produce photons with 511 keV, but they will recharge redshifted. So they will not contribute to the 511 keV line, but they will contribute to the cosmic X-ray background, which has been measured by different experiments such as EAO and SMM. And actually also in this case, here you can see the experimental data and the Alp-induced flux. And also here we can constrain the Alp parameter space by requiring that the Alp-induced signal must not be larger than the experimental data. And the most constraining limits are obtained through SMM. So here you can see now an overview of the axion of the bound on the axion electron coupling as a function of the axion proton coupling obtained using the 511 keV line. So you can see that we can exclude a wide range of the Alp parameter space. And for even larger values of the coupling, the parameter space can be excluded using the supernova energy explosion argument that I described before for axions interacting with photons. So now this is the last slide. I would like just to thank you for the attention. And as we have seen together, we can use supernovae to probe axions interacting with a lot with different standard model particles in the wide range of masses. So with this, I conclude, and I would like to thank you for your attention. Some other questions? Oh, okay. Actually, I mean, we did a work. I have not backup slide with this, but in principle, axions could be produced also in the strong magnetic fields inside the supernova. And actually, heavy Alps with masses of the order of the MeV can be resonantly produced when the plasma frequency matches the axion mass. So in this case, in principle, they can be produced there, and then they could decay, leading to an observable gamma ray signal. And we have done work. Yeah, exactly. Actually, we consider this in hypernovae, which is a supernova with a very high magnetic field, actually. And we have done this paper in which, in principle, in the case of an explosion of a future hypernova, there is a region of the parameter space which could be probed through the observation. No, we don't. No, because in that case, there is no resonant production. So we need heavy Alps to obtain a resonant production in that case.